Let's say your calculus teacher asks you to find the derivative of x squared plus y squared equals 100. Up until now, everything you're familiar with involves functions of the form f of x equals some function of x, say x squared, or ln of x plus sine x or something like that. And for this, you'd use the chain rule. You'd use the sum rule and then the chain rule and differentiate it that way. But what would you do if you don't have a function explicitly defined as a function of x? How would you find the derivative with respect to x? Well, to do that, we use a technique called implicit differentiation. And basically what this exploits is that here y is actually implicitly defined as a function of x. So y is implicitly a function of x. So what we do, the basic technique is we differentiate. So we have x squared plus y squared equals 100. We differentiate this side with respect to x, so we take d dx of the left side, and we take d dx of the right side, and we set them equal to one another. Because the derivative is just an operation, right? So if two sides are equal, two sides of an equation are equal, then their derivatives must also be equal. So in this case, what we'd if we wanted to find the derivative of the left side, derivative of x squared is 2x, right? But now y squared is implicitly, remember y is implicitly a function of x. So first what's the derivative of y squared with respect to y? Well, that's 2y. But y is implicitly a function of x. So we have to use the chain rule here and multiply by dy dx. And on the right side, we just have a constant, so that's 0. So when we work these implicit differentiation problems, we collect all the dy dx terms on one side. So on the left side, we'll collect 2y dy dx, and on the right side, we'll have negative 2x. So then dy dx is equal to negative x over y. Now let's see if this slope makes sense. So we know that x squared plus y squared equals 100. It's going to be a circle with radius 10, right? A circle centered at the origin with radius 10. So we basically have something like this, and we're checking points on the circle. Let's check 10, 0. The slope at 10, 0 is, well, dy dx is negative 10 over 0 is infinity, right? And that seems to be correct. Now what about at 0, 10? Slope should be 0, right? So slope is negative x over y, negative 0 is 0 over 10, and that's 0. Now what about here where theta is 45 degrees? So this would be 10 times the cosine of 45 degrees, comma 10 times the sine of 45 degrees. That would be the point we're looking at here. And remember, cosine of 45 and sine of 45 are both root 2 over 2, right? So dy dx, that'll equal -10 times the square root of 2 over 2 divided by y would be +10 times the square root of 2 over 2, and that's just -1, and it looks like the slope is indeed -1 here. It looks like the line tangent to this is a line with slope -1. We'll now look at a slightly more complicated example. Say we wanted to differentiate x sine y. We had this implicitly defined function of x, which is x sine y plus y sine x equals 1. And we didn't know, we weren't able to define y in terms of x, but we still wanted to find the rate of change of y with respect to x. To do that, we'd have to use implicit differentiation. So we differentiate this side with respect to x, find the derivative with respect to the left side, and that would be equal to the derivative with respect to x of the right side. So first we'll look at this term here. See, we use the product rule, so we find so this is the derivative of x sine y. I'm just going to go ahead and write everything out. Plus the derivative with respect to x of y sine x equals the derivative with respect to x of 1. We can just look and see that this is 0, right? The derivative with respect to a constant is always 0. Okay, now focusing our attention on this first term here, this x sine y term, if we want to differentiate that with respect to x, we'll see we have to use the product rule, right? So that'll be the derivative of x with respect to x times sine of y plus x times the derivative of sine of y with respect to x. So that will be x times the cosine of y dy dx. This is using the chain rule again. We wrote down the x. This is the first times the derivative of the second, right? So the derivative of sine y is cosine of y times dy dx, because we're interested in the derivative with respect to x. If we differentiate sine y with respect to y, we get cosine of y, but y is implicitly a function of x, so you have to multiply by the derivative of y with respect to x, since we're differentiating this whole thing with respect to x, right? And then we sum that to the derivative of the first function here, which is just x, times the second function. We just write down the second function. Okay, and then the derivative of y sine x. Well, here we use the product rule again. This is just y times the derivative of sine of x with respect to x. That's y cosine of x. Plus the derivative of y with respect to x is dy dx times sine of x. We just write sine of x down. Equals 0. Now we collect the dy dx terms on one side. So from here we have x times the cosine of y. That's multiplied by dy dx. Here we just have sine of x. And on this side, we have the other terms that are not multiplied by dy dx. So this is negative sine of y minus y cosine of x. So at this point we can divide both sides by x cosine of y plus sine of x to solve for dy dx. So we get dy dx equals negative sine of y minus y cosine of x over x cosine of y plus sine of x. And if you're asked to find the rate of change of this function at any particular point, rate of change of y with respect to x for this function at any particular point, all you have to do is plug into this expression for dy dx. So if we wanted to find the rate of change at, say, 2, 1, we just plug in 1 for y and 2 for x.